Hi, I'd like to start with a comparison of two results that we have covered in two other videos. Number one, if an n by n matrix A has n linearly independent eigenvectors, then there exists an invertible n by n matrix P such that A is P times D times P inverse for some diagonal matrix D. Secondly, if a real 2 by 2 matrix A has complex eigenvalues A plus or minus IB, with B unequal to 0, then there exists an invertible 2 by 2 matrix P such that A is P times C times P inverse for some rotation scaling matrix C. What do these two results have in common? Well, although a diagonal matrix D is not the same as a rotation scaling matrix C, the two decompositions clearly have the same structure. These two formulas are two examples of a so-called similarity relation between two matrices, which is the topic of this video. Here's the general definition. Two n by n matrices A and B are similar if there exists an invertible n by n matrix P such that A is P times B times P inverse. Note that similarity of A and B is a symmetric property because of the equivalence shown here. Although we have two different symbols, P and Q here, the two formulas obviously have the same structure. Given two similar matrices A and B, the transformation which sends A to B is called a similarity transformation. Similar matrices have many properties in common. The main result in this video will be the following theorem. If a matrix is subjected to a similarity transformation, then the eigenvalues and their multiplicities, both the algebraic and the geometric ones, are preserved. To prove this, let's start with the geometric side of the story. Suppose A is P times B times P inverse. Consider the linear transformation which sends a vector x to A times x. Now, multiply both the vector x and the vector A times x with the matrix P inverse. Now the vector P inverse times A times x can be obtained from P inverse times x by matrix multiplication. Which matrix does this job? The answer to this rhetorical question is, of course, B. Indeed, B times P inverse times x is equal to P inverse times A times x, due to the implication shown here. So, if we multiply the vector P inverse times x with the matrix B, then we obtain the vector P inverse times A times x. What is the meaning of these two vectors? Well, if the matrix P has V1 up till Vn as its columns, then P inverse times x is equal to the coordinate vector of x with respect to the basis V1 up to Vn. And similarly for the vector P inverse times A times x. Hence, if T is the linear transformation with standard matrix A, then B is the matrix of T with respect to the basis V1 up till Vn. This is why the matrix P is often referred to as the change of basis matrix. With this schematic representation of the relation between A and B, it is very easy to prove the following theorem. If A is equal to P times B times P inverse, then A times V is lambda times V if and only if B times P inverse times V is equal to lambda times P inverse times V. Here's the proof. Consider the schematic representation with V in the upper left corner. Since A times V is equal to lambda times V, the figure can be replaced by the one shown here. Finally, if we interchange the matrix P inverse and the number lambda, the required equation becomes visible in the bottom row. Hence, if A is equal to P times B times P inverse, then A and B have the same eigenvalues, And secondly, V is an eigenvector of A with eigenvalue lambda I, if and only if P inverse times V is an eigenvector of B with eigenvalue lambda I. Note that P inverse times V cannot be the zero vector if V is unequal to 0, because the matrix P inverse is an invertible matrix. Also note that this property can be generalized to the property shown here due to the fact that P inverse is an invertible matrix. This implies that the dimension of the eigenspace of A associated to the eigenvalue lambda I is equal to the dimension of the eigenspace of B associated to the eigenvalue lambda I. Recall that the dimension of an eigenspace is equal to the so-called geometric multiplicity of the corresponding eigenvalue. Now I will show you that the algebraic multiplicities of the eigenvalues are preserved as well. Here's the theorem from which that follows. If A is P times B inverse, then the determinant of A minus lambda times I is equal to the determinant of B minus lambda times I. Here's the proof of that theorem. Firstly, the matrix A minus lambda times I is seen to be equal to the matrix P times B minus lambda times I times P inverse. Hence, due to the multiplication rule of determinants, the determinant of A minus lambda times I is equal to the product of the three determinants shown here, which is equal to the required result due to the cancellation indicated here. Hence, if A is equal to P times B inverse, then A and B have the same characteristic polynomial. This implies that the multiplicity of each shared root of that polynomial is the same for A as for B. Recall that this multiplicity is called the algebraic multiplicity of the eigenvalue in question. Let's put the results together in the following theorem. If a matrix is subjected to a similarity transformation, then the eigenvalues and their multiplicities, algebraic and geometric, are preserved. Hence, two matrices A and B cannot be similar if A and B do not have the same characteristic polynomial, or A and B do have the same characteristic polynomial, but for at least one of the shared eigenvalues, the geometric multiplicities are not the same. So in short, similar matrices have the same eigenvalue with the same multiplicities, algebraic and geometric. Conversely, if two matrices have the same eigenvalues with the same multiplicities, algebraic and geometric, are they necessarily similar? The answer is no. Here's an example of two non-similar matrices that share all eigenvalues and their multiplicities. Indeed, both A and B have one eigenvalue 0 with algebraic multiplicity equal to 4 and geometric multiplicity equal to 2. But there is no invertible matrix P such that A is equal to P times B times P inverse. You can easily check that the equality A times P is P times B implies that the second column of P is equal to the 0 column, so P cannot be invertible. Let me round off the video. I hope that whenever you come across a similarity relation between two matrices A and B in the future, that you will remember two things. Namely, first of all, this schematic representation, which tells you that A and B are two matrix representations of the same linear transformation. Secondly, the fact that A and B have the same eigenvalues with the same multiplicities.